We give an introduction also to introduce the quantum information, how it works, starting by the classical information. The carrier of classical information is called bit. A bit means that our system can be in definite state 0 or 1. But on the other hand, a qubit is different thing. So our physical system can be in state 0, in definite state 0 or 1, or in all possible linear combination between 0 and 1. And we can write it like, we can write it like you see here. So our state is can be written 0, 1, alpha and beta represent the probability amplitude of our system to be in state 0 or 1. What happens if we add 1 qubit to our system? If we add our 1 qubit to our system, so our state can be in superposition of four possible states. Like see here is 0, 0, 0, 0, 1, 1, 0, and 1, 1. If we add another qubit, so everything is doubled. Everything. So the power of the quantum computer is going to be doubled whenever we say we add 1 qubit. So the beauty of quantum computation is coming from the weirdness of quantum mechanics, and even what to involve supersymmetry in this quantum computer or quantum computation by introducing what we call here a superqubit. What is superqubit? Superqubit is a minimal supersymmetric extension of what we call qubit. It's an element from super Hilbert space. It can be written as you see, it has some unusual properties like crossing series bound and other things. We can write it as you see here in the our system can be 0 and 1 and dot here. 0 and 1 and dot are the computation basis for our super Hilbert space. A1, A2 are even or commuting Grassmann numbers, and A dot is anti-commuting Grassmann number. To remember what is Grassmann number, Grassmann number can be written in this forms as the body and the soul. The body, when we say Grassmann number over C, so the body here is a complex number, and the soul is product of Grassmann variables. When it is the product is even, we call it even Grassmann number, and if the Grassmann variables, the product, the number of Grassmann variables is even, we can, is odd. This is the odd part of Grassmann number. So we cannot compute with only one superqubit. We need more than one. So we can get the 2 superqubit by a tensor product of 1 superqubit, 2 superqubits. Like you see here, this is the state of 2 superqubit, and A, B, and A dot dot are, we say, commuting Grassmann numbers or even Grassmann numbers. Also, these are anti-commuting or even Grassmann numbers. So in the general case, we can get a tensor product. We can get multi-superqubits by tensor product of 2 or more superqubits. So, as in conventional quantum mechanics, 2 states can be entangled. It means that we cannot write our state as a tensor product of its constituent. So also this idea is accepted to super entanglement, where our system is like this. But this state cannot be written as a tensor product of its 2 constituents. Also why this is easy to see that we cannot get a complex number from 2 or from the product of 2 Grassmann numbers. And this is interpolation between the two. The first state is called the maximally superentangled state. So we have superqubits, and we need to process them using supergates. The idea of supergates is extended. So gates is the basic operation over superqubits. We can represent them as super matrices, as you see here. super matrices are elements from a unitary orthosymplectic supergroup. And this is the schema. Also we can, this is a single superqubit. We involve also controlled superqubit in our quantum computation. This is the table of reality, and this is controlled super gates, where the first superqubit is the control and the second is a target. Also, we can extend, do extend the conventional gates in quantum mechanics to super C0 gates. It's working in different logic, but no. So also Toffoli gate is controlled by AB, and the target is the third superqubit. Using these two superqubits and the super gates, we need to perform something usual in quantum information, the teleportation. Teleportation means that we can teleport or send one qubit from one location to another without passing through space. And the idea is extended with using super teleportation. Alice want to send, like see here, as this is the state which we need to teleport, and this is pre-shared superentangled state. This is a circuit that we use here in our super gates. We have the input, the state that we need, or super state that we need to teleport, and this is a pre-shared superentangled, maximally superentangled state between Alice and Bob. After doing some operations using these superqubits, our output is like this. The result is depend on the measurement. After the Alice measure his superqubit, he communicate with Bob to give the result, and Bob, after depending on the result, he will do the operation needed to teleport this. The idea also have been done with a super dense coding. Super dense coding is invented by Bennett and Wisner in 1992, I think. The idea is how can they exchange the 2 bits, or how they exchange 2 bits between 2 parts using only 1 qubit. Here we do some operations to send 3 classical bits by sending only 1 superqubit. This is so the sender send only 1 superqubit by the help by the help of superentangled pair. They can send 3 classical bits. And this is the circuits that we designed. We have the input here, and the output we can interpret. This is one of the 8 possible cases that we have. We have 8 cases to send 3 classical bits, and this is our circuit. Finally, we conclude that superquantum information and computation is a very interesting field of research. It combines beauty of supersymmetry and the strangeness of quantum mechanics. In the future research, we will try to write a known algorithm in the version of supersymmetric version, and will involve superqubits maybe in the field of cryptography.